All right, I see more people are coming in, so I think I'm going to get started. So just first of all, just good afternoon and just welcome to everyone that is joining us today for the webinar on offshore wind in Atlantic Canada. My name is Elisa Oberman and I'm the Executive Director at Marine Renewables Canada, and I'm also going to be your host and moderator for today. So as we get started, I would like to begin by acknowledging that we are hosting this event from Mi'kma'ki, the ancestral and unceded territory of the Mi'kmaq people, and we acknowledge them as the past, present, and future caretakers of this land. So as a lot of you have probably seen, and why there's interest in today's topic, is offshore wind is gaining quite a bit of momentum as a renewable energy resource that can play a role in energy transition globally, but now we're hearing a lot more about it in Canada as well. So as it becomes more of a focus in Atlantic Canada, we really wanted to build on some of the webinars that Marine Renewables Canada has previously had that focused on offshore wind opportunities in the United States and where that market's going, by starting to help our members and network learn more about the opportunity in Canada and also for this region in particular. So today, I am very pleased to welcome Jordan Eamer, who is marine geoscientist working at the Geological Survey of Canada at the Bedford Institute of Oceanography in Dartmouth, Nova Scotia. And today, Jordan is going to provide us with an overview of some of the preliminary work that's been conducted to assess geological constraints and opportunities with regards to offshore wind in Atlantic Canada. So just quickly, kind of a housekeeping matter in terms of format, and I'm sure everybody on this is very familiar with this by now, but I thought I would just say it. We're going to have a Q&A portion at the end of the webinar, so it will follow the presentation. But throughout the talk, feel free to put in any questions that you may have in the Q&A or chat function, just as you're thinking about them, so you don't lose the thought, and I will do my best to get to them at the end. So over to you, Jordan.
Thanks so much. Thanks for the intro, and get this going here. Have I got the right screen, or should I switch it?
Switch it. It's showing the notes. Yeah.
How's that?
Perfect.
All right, great. So thanks for the introduction, and thanks everyone for joining. I had a brief look at the registrant list today. There's a pretty wide range of backgrounds and affiliations. So it's neat to see that kind of interest, but pretty tough to plan a talk for. So I'll try to skirt super detailed descriptions of geology or industry while getting more into some of the interpretation of the data in Atlantic Canada that we have to work with. So first off, I like to use this photo to get everybody thinking about scale. So what we're looking at here is about the average size of an offshore wind farm in Europe. And we're only seeing 30 of 54 of the turbines. So each of these turbines has a foundation that's placed on or in the seabed with cables on or under the seabed that connect all of them, all routed to a substation or two that, which you guessed it, is on a foundation in the seabed, and then a large landfalling cable that has to navigate all sorts of geology to get to the coast. So knowledge of the seabed geology is important. It's paramount. And since we have established world-class wind resources in Atlantic Canada, we have begun, the GSC, have begun desktop studies to assess what the foundation conditions in Canada's offshore amount to. So first, a bit on the market. So in the US, they're on pace for 35 gigawatts of offshore wind by 2030. With only 40 megawatts operating today. So if you look down in the bottom left of that graph, at that little orange sliver, which itself is a subset of the tiny sliver on the main graph itself, that represents the first 2 turbines that are operating federal waters in offshore Virginia. These types of leases make up the majority of the activity that you find in this region. The UK has been a major player since their first turbines went offshore in December of 2000. In the 20 or so years that have followed, they have added more than 10 gigawatts of capacity in offshore wind. And they have just set the bar. They're looking for 50 gigawatts of capacity by 2030, which is a pretty dramatic ramping up of capacity. if we put that in perspective with Canada's electricity generation, we averaged about 72.5 gigawatts of electricity generation nationally across the whole country in 2019. But I do want to point out the crudeness of this estimation. I am a geologist after all. And the most up-to-date estimate of generating capacity puts it, so this is the total electricity that we can generate in Canada in 2017 was 145 gigawatts. So I'm sure this has changed in the intervening 5 years, but it's still relevant for comparing values to that 50 gigawatt target and 35 gigawatt target for offshore wind capacity in the UK and US respectively by 2030. So really briefly, why offshore wind? So one thing that is true everywhere is that winds offshore are stronger and more consistent than onshore. In densely populated areas such as the US and UK, large farms can be situated close to high demand. This is not really applicable in Atlantic Canada, which is fairly rural in some ways, but additionally, this industry can provide new opportunities for marine-based industries and employees that are otherwise impacted by policy change or climate change. And there is perhaps more social license if you just simply consider out of sight, out of mind, but there are certainly notable exceptions to that last one. So with that, there is notable signaled interest in Canada, including the development of federal regulations for offshore renewables and offshore wind, a strong pivot of marine regulatory agencies toward renewables, a public announcement of a regional environmental assessment launched for offshore Nova Scotia and Newfoundland for offshore wind, and some renewed industry interest in Canada. Okay, so that's the industry side. There's lots of offshore wind globally producing power or in development. There's support building in Canada, and there are excellent wind resources in Atlantic Canada. So before we do a detailed dive into some sort of site-specific areas of our offshore, I think it's prudent that we have a bit of a geology 101. So my apologies if most of you know this, so I'll be quick. But so if we look at sort of three main factors that create the conditions that we find in our continental shelf. The first one is that the continental shelf lining the Atlantic Ocean is almost entirely what's called a passive margin, which generally leads to broad, flat shelves with thick sedimentary sequences, like you see in the top left there. This is in contrast with most of the Pacific, where subduction results in an active margin, which is characterized by narrower, rugged shelf and volcanic rocks. So with that description, it's perhaps not surprising that the bulk of offshore wind is located on passive margins with their thick sediments and broad flat areas. And there's a few notable exceptions like in China, but that's a talk for another time. Okay, so that underpins the broad shape of our shelf in Atlantic Canada. After that, there are two major forces influencing the geology of the seabed. The first is previous ice ages, continental scale ice sheets that advanced and retreated from our marine areas several times in the past couple million years. The most previous maximum extent of ice happened around 20,000 years ago and extended about to our shelf edge. This ice, in some places kilometers thick, heavily eroded soft sediments in some places and deposited thick packages of sediments elsewhere. And as that ice retreated over thousands of years, it deposited huge volumes of sediments in our offshore banks and carved out deep channels on our shelves. So this gives us our broad distribution of sediments on our shelves, which is important for water depths and finding sediments to bury foundations and cables. Okay, so now we have a broad shelf shape and a general idea of how the sediments got carved out from some places and dumped in others. The final major factor in offshore geology, particularly important in Atlantic Canada, is the dramatic changes in sea levels that followed these ice ages. So I'm really happy to go through the nitty-gritty of relative sea level change. That's my jam. if somebody wants to ask after. But for our purposes and the purposes of time, it's mostly important to know that for the most part, sea levels, as ice was retreating, were much lower, on the order of hundreds to tens of meters lower than present. So as you can see in this picture, this map of all the land surface, which is in green from 13,000 years ago, you see much of the outer banks was subaerial at that time. So over those 13,000 years, it rose to present. For some of these regions, the low stand came a little bit later. For instance, around PEI, the Northumberland Strait and the Magdalen, sea levels became lower around 9,000 years, but then again, slowly rose to present. So this process is important if you think about our coastline right now, with waves, tides, currents. It's very energetic, lots of sediment being eroded, moved, and deposited elsewhere. So this is important on our shelf and for foundation conditions, where as the coast migrated across all of these areas that were once land, much of the accessible sediments were removed or reworked into lower basins, leaving rugged bedrock in its place. And this is really, really common on our shelves. So I really want to quickly point out the differences between Atlantic Canada. In the middle, we have the North Sea. You can see the UK, France, Norway there. And then on the very right, we have the US Atlantic coast. So the color scales for the bathymetry here are all the same. So darker colors mean deeper water. And you can see that deeper water on the shelves of Atlantic Canada are more prevalent than the shelves of these other two regions. Also, if you trace that blue line there, which is the outline of the maximum extent of ice at the last glacial maximum, much of the North Sea and US Atlantic coast were actually unglaciated at the last maximum. So that leads to a much different geology than we find here in Atlantic Canada. Okay, so why is all this geology important? Well, because it's cool, in my opinion. But also offshore wind turbines are fixed to the seabed through a foundation. Most likely what's in the top left, a monopile foundation, which makes up about 80% of all offshore wind turbine foundations. So that bottom section being fed onto the barge there, that's the part that needs to be driven into the seabed. So you need that much ideal sediment for each one of these foundations. If we go clockwise around the slide, we see jackets on suction caissons in Scotland. In the bottom middle there, we have concrete gravity bases that just sit on the seabed. Those are being manufactured in France. And in the bottom left, we have all the components of two offshore wind turbines. I actually took this picture in Halifax Harbor here. These were destined for Virginia, where they currently operate as the first two turbines in federal waters. And that was that orange sliver that we saw on that graph on an earlier slide. I won't discuss floating offshore wind much today, but happy to address any questions that I can answer in the chat afterwards. I will say, though, that even though costs remain quite high, there's pretty much a concrete bet in the market that floating is going to become a major component of the offshore wind mix. So these are all the possible planned or developed floating offshore wind developments globally. And I've circled all the black ones, which are the ones that are currently in operation. So not a lot of them, but there's a lot in the mix here. These are all still basically considered demonstration, the ones that are operating. They're just a few turbines at most. Another quick note on floating offshore wind. While it pretty much removes the water depth consideration, you still need to anchor each one of the turbines. Sometimes 3 anchors per turbine. So seabed geology is still vital to emplacement. In general, foundations that are attached to the seabed are in waters shallower than 60 meters and within about 200 kilometers of shore, which puts much of Canada's continental shelf into play. In the middle here is a diagram of those common foundations that we saw on a previous slide, and it shows how important the offshore geology is. You have to have accurate water depths, and you need to know what you're going to find below the seabed to keep those foundations in place safely and efficiently. So as marine geoscientists, we can contribute that data on the seabed, vital for these applications, through methods that we have employed for decades, like those that we see on the right. So at the GSC, we have decades of legacy data to draw upon, and I unfortunately can't really go into all of these due to time, but other than to point out that we can use modern survey data such as multi-beam to create detailed bathymetry like we have in the center there. But we can also use what's called backscatter to get an idea of what types of sediment we might find on the seabed. That's on the bottom image. Both of those are from Long Harbor, Newfoundland. We have very nice high resolution seismic data that can give us information on subsurface stratigraphy, boulders, bedrock knolls, glacial moraines, like we see sort of in the banner across the top there. And the modern Huntex systems from which this is an image from, we have access to collect really incredible high resolution data. And finally, we have a very capable geotechnical lab that I would like to get rolling on characterizing our shelf sediments. And the middle right here is a Canadian Hydrographic Service data portal with the website there, where you can get bathymetric LiDAR and multi-beam data downscaled to 10-meter resolution. But I do want to point out, if you look at the big broad area of the shelf there off of Nova Scotia, and you compare that coverage or lack of to the Northeast US or the UK and their high resolution data sets that they have to work with, you can see we're kind of hamstrung here in Atlantic Canada. We've got a big shelf, not a lot of ships, and our efforts have been mostly elsewhere until this point. So that will have to change if we're going to fully get a handle on the offshore wind in our area. But we do have some new tools coming online, like a multi-sensor autonomous submarine that can map at 50 centimeter resolution or better, as well as create subsurface data, cameras, and all sorts of things. So this image on the right here is out of the Bedford Basin, and you can see the complex seabed anchor scours that are not visible on a typical 2-meter resolution multi-beam, which it's overlain on. Okay, so we want to know water depth and thickness of sediments, but we also need to know what they are and their properties, their geotechnical properties. So muds and glacial tills, for example, can be challenging for foundations due to their geotechnical properties, or gases in the muds, which can be a geohazard, or boulders in the till, which can be challenging for foundation and placement. Geohazards are important. You can see on the right, the seabed map collected 2 years after installation of the Scroby Sands wind farm in the UK. You can see several meters of scour around each one of the turbine foundations. You can easily pick out each one of those locations of the turbine foundations there. The seabed dunes here at the scale of tens of meters tall and kilometers long indicated those strong currents in the area. Sometimes there are whole other considerations, like in the middle here, where archaeology, unexploded munitions might be an issue, where these World War II era shipwrecks were found in an offshore wind area off Virginia. Okay, so that's primer. And now I suspect what many of you came for today, we'll start looking at site scale areas in Atlantic Canada. So for the rest of the slides, for the most part, the layout will be consistent. So you can locate yourself in Atlantic Canada on the left, and then available data is on the right. So as you'd expect, high resolution mapping data are generally these little postage stamps, and we'll supplement this interpretation with seismics or other ancillary data. So if we start in the Bay de Chaleur in the Western Gulf, it has a basin of thick post-glacial muds. So it's that top unit in the seismic there that looks fairly clear. It's silts and fine sands. And it's occasionally broken up by superficial expressions of glacial sediments, such as this moraine that you find in the multi-beam here. Post-glacial muds are often not great foundation sediments. They have very low shear strengths. They can be highly compressible, and much of it is unstable due to that subsurface gas. Very shallow areas, like we see in the north of the multi-beam here, experienced a bit of low sea levels, so they have some relic coastal features and sands and gravels from that wave action, but they're not appreciably thick. If we move to the New Brunswick coastline, there is unfortunately next to no data in the area, but it is quite shallow and fairly flat. However, the seabed is mostly just a few meters of sand and gravel right on bedrock. So if you follow this seismic data here, you can see that there is the occasional channel at A that becomes infilled with tens of meters of sand, but they're fairly few and far between. Nearer to shore, there may be large, thick sandbanks as indicated by the sedimentary coastline. We just don't have the data to support that. If we move to the Northumberland Strait, we can pretty confidently say that gravity-based foundations can be successful there, as there are many of them in place supporting the Confederation Bridge. Where the seabed is composed of glacial sediments, they have the right properties to support that type of foundation. The multi-beam image here showing that you can see that heavily pitted and scoured glacial surface that is supporting that bridge. Elsewhere, like this seismic section from further east in the strait, a few meters of mud, that sort of semi-translucent section above the bedrock, which is that harder surface, that may be a challenge for any type of emplacement. The shelf area north of the Prince Edward Island is shallow and fairly flat. However, as you can see from this seabed map here, it's nearly devoid of sediment in much of it. So sand has been redistributed into channels and basins from that sea level, the coastline migrating over this whole area when sea levels were rising post-glacially. And where it does accumulate, it may not be very thick. Bedrock is high relief and often cut by what might be, what would have been rivers when sea levels were lower. The shelf surrounding the Magdalens is very complex. Actually, in my opinion, the mapping data is quite beautiful. Where bedrock is exposed, it's tightly folded and overturned, and often even fractured into smaller chunks. Salt diapers, these are large subsurface domes of salt that intrude into the rock and sediment above, have caused all sorts of deformation. In the map on the right here, you can see those circular structures are actually where those salt domes have intruded through the superficial bedrock and sediments. Elsewhere though, like in the central map, you can see thin, sandy, smooth sheets that would be just overlain over bedrock. And some of these sandy sheets, like in the top right, are organized into current swept sand waves and dunes, showing the mobility of some of those sediments. Off of East Point, Prince Edward Island, there's a sandbank called Milne Bank. The sands there are likely tens of meters thick. The bank itself is relatively flat and it's quite close to shore. Again, dunes moving at several meters per year in the northern portion of the bank. They are moving towards the south. Would indicate challenges for foundation emplacement. But this is the first site that we've looked at thus far that you could conceivably say monopiles, which is that industry standard for foundations, might be feasible. This is a similar environment to many of the banks found in the UK region of the North Sea. So if we swing around to the eastern shore of Nova Scotia, a patch of multi-beam has been worked up by my colleague Ned King at the GSC into a detailed superficial geology and stratigraphic interpretation. There's a lot going on here, but this is very typical of the Nova Scotian inner shelf, in some ways similar to what we saw off of the northern Prince Edward Island. So much of the sediment was reworked during that sea level rise, that coastline migrating over this part of the shelf, so that there is lots of exposed bedrock, rugged exposed bedrock that you see there in pink. Former river channels, again formed in at lower sea levels, are filled in with sand in yellow there. And as you move into deeper water, here at about 100 meters water depth, you start to see those ice contact sediments or that glacial till that is really high relief and would be really challenging sediments. Muds in blue are found in the deepest portions. Mostly, however, sediments across this whole profile aren't much thicker than a few tens of meters, and the surface and subsurface are very heterogeneous. If we move to the south shore of Nova Scotia, the seabed at shallower depths is fairly similar to what we saw further east, with large regional moraines. You can see those large ridges that are almost curvilinear there, composed of glacial till, and there's lots of exposed bedrock. Again, if you look at the superficial geology sort of inset map there, that bedrock is pink. There's thin sand sheets in yellow, cover bedrock in places. And that post-glacial, that mud unit, the blue is fairly rare. We move, oh, right. I did want to point out that even as you move closer to shore, we've got some bathymetric lidar here. Exposed bedrock is still very common, as you can see in this rugged seabed image from bathymetric lidar from CHS. Even though you're surrounding Cape Sable Island, you suspect lots of sand, but it's just infilling the basins in between the bedrock. Excuse me. Browns Bank, which is just off the south shore, is fairly shallow as 30 meters. However, the shallowest portions are mostly a moraine composed of glacial till. You can see in that side scan image, it's just kind of like a picture of the seabed on the bottom right. You can see a number of boulders across that moraine. So that section is highlighted in red on the multi-beam in the top right. On the south side of the moraine, so as you move away from the ice, thicker sands and silts are found, which may be suitable for foundations, but hazards again would be a problem. You can see mobile sediments, so you can see a sand wave field, and again, boulders are a problem. Okay, so if we go east and we're in those outer banks near the ice edge now, Sable Bank, it's shallow, much of it's less than 30 meters and a huge area is less than 60 meters. It's composed of very thick sands with some exceptions in some of the geologic profiles that have been done. And much of it exhibits a characteristic ridge and swale topography that, for example, you would find in that Virginia offshore wind area with large sand waves that are common. The mobility of the sediments here are well studied and can be accounted for in site design. And we know piles work here. Oil and gas platforms use them here for years. We also have good seismic and geotechnical data on the sediments and stratigraphy for Sable Bank. Anchor Row is Sable Bank's sort of less understood cousin, also near that outer ice margin, also exposed at the sea level low stand. It is, however, a little deeper. None of it is shallower than 30 meters, and there is much less data. What we do know, though, is that there are several infilled channels that cut through it, and generally the sands and silts here are very thick. Bathymetry is quite subdued, and there are less of those sand waves. But without detailed mapping, it's hard to say more. If we cross over the Laurentian Channel, we find St. Pierre Bank. It's flat. It's got a similar water depths to Bankero. And if you look at the bottom, the superficial geology is sand and gravel, similar to those two other outer banks. However, if we look at the top center here, detailed work on the subsurface geology suggests that the depths of sediments on this bank can be highly variable from exposed bedrock to 50 meters of sediment at most. On to Newfoundland. St. George's Bay in Western Newfoundland has a moraine across the bay that's quite shallow and extensive, and essentially has been planed flat by wave action and sea levels that dropped a bit below present. You can see those lobes of sediment that have been reworked and pushed off into the basin towards the east there. Much of the geology here is similar to Smith Bank in the North Sea, and Block Island in the US, areas with developed offshore wind. The geology is mostly associated with sandy tills. Here, subsurface boulders could be a problem, have been identified in published literature. And St. George's has been associated with offshore wind in a past proposal in the top right there. That got some investment and some interest. And very recently, I think this was 2 days ago, in the center here, has seen renewed interest in this type of industrial activity. So Western Newfoundland has some areas with shallow seabed, but again, glacial till in the top, the Bay of Islands there, is very high relief and would be challenging for foundations. Areas with deeper sedimentation like Port Bay have mixed geology, muds, sands, and gravels, but the muds can be gas charged. So a geohazard there. I want to note that graduate student at Memorial, Caroline Lee under Sean Mullen, is producing a detailed seabed map of the whole Bay of Islands area with a focus on offshore renewables. So keep an eye out for that. The other broad areas of shelf in Newfoundland are generally pretty bouldery, or the sediments are very thin. And both of these would see problems with icebergs as well, which can be engineered against. There are offshore wind platforms or installations in Finland that are ice resistant, but it's costly. So very quickly, as I wrap up here, I just want to point out what work is ongoing. So we plan on releasing a detailed assessment of the continental shelf of Pacific Canada with a focus on offshore renewable infrastructure later this year. This includes the beginning of a geotechnical database, for which we are just beginning the lab work this week, actually. We're finishing off an isopack map, or depth of sediment map, similar to what we saw, which I had a screen grab of for St. Pierre there, which will provide critical data for any offshore infrastructure emplacement. This will expand our mapping efforts to make a continuous map from southern Newfoundland through central Nova Scotia, which are obviously areas of interest in this latest push for offshore wind. And as we refine our work, we're going to apply a fairly new approach to suitability modeling, where we can rule in or out foundation types based on multiple proxies, summarized in considerations tables, where you can select foundation types based on input data. And it just so happens that the GSC program that this work falls under, there are other really smart GSC researchers that are publishing data that are seemingly tailor-made for identifying sites for offshore wind. So these will form a foundation for a series of useful, innovative suitability maps for our shelves coming soon. We have an honor student from Acadia that just started building on earlier work to investigate a potentially unrealized risk of subsea landslides and what causes them in this area in the red circle on the Eastern Scotian Shelf. This has obvious implications for offshore foundations and cables. And now that we have identified areas with high potential, hopefully we can go and actively collect data and develop geological models to support future environmental assessments or de-risk investment in this area to help support this source of renewable energy. So I really want to end with just kind of a laundry list of burning questions that I'm not yet trying to answer, but do want to work towards. I'll just blast through these really quickly, and see I'm running a bit over time. So we need to build up more geotechnical data on our shelves. We need a better handle on the characteristics of the tertiary rock in our offshore region and whether it can accept foundations. We need to better understand the Eastern Scotian Shelf Tunnel Valley Complex, which is perhaps globally unique. And there are many offshore wind farms in the North Sea that are built on tunnel valley complexes. Another question is, if we find drowned estuary sediments like we expect off of much of Nova Scotia's coastline, what does that mean for foundation stability? They can be inherently hazardous. And I covered the salt diaper question earlier, but finally, what are we going to find when we start mapping these big blank areas of our shelf? And with that, I'll wrap it up. So please feel free to check out what's already out there, and stay tuned for some stuff that's on the docket. Thanks very much.
Great, thanks so much, Jordan. So we're going to go, we have some questions, but one thing I just wanted to ask before we got into that, and also I would also going to say thank you for the Geology 101 part in the beginning, because as a non-technical person, it was very helpful for me. So it made the rest
Perfect.
of the presentation probably more relevant.
I'll mail out a certificate.
Okay, good. So one of the questions I had, that last slide you had with the, the kind of like, what are the next steps or next kind of questions that you would be looking to answer? How does, and I don't know if you can answer that completely at this point, but how would something, that kind of, those kind of research questions be prioritized within the GSC? Is it driven by, industry looking for that information, or are there other drivers in how that gets done?
Yeah, so I kind of included this laundry list of questions because they're sort of, I think if I go back one more slide, I think this kind of geological model that's on the right here, this is for an offshore wind farm in Norway, and it was just published. I think this is probably priority number one, where we go in and we do this integrated approach and we look at all the different factors geologically for a site. We're not necessarily going to pick a site for offshore wind, but we're going to sort of see this is the kind of work that we can do to support this. I think that would be priority number one. And these are the kinds of things that I think are very relevant for our offshore, but some of them might be kind of niche. So for instance, if most of the interest for offshore wind comes off of Nova Scotia, salt diapers are a non-issue. Those are found in the Gulf all the way up to St. George's Bay. So some of these may be shelved depending on where the interest actually lies. And I think that some of this regional environmental assessment may drive some of this work. So it'll be more on the geotechnical properties and the tertiary bedrock, which can be exposed in a lot of these areas that may drive a lot of what we're looking at. And again, it's kind of, if we're looking closer to shore, those organic sediments become a factor, but if we're looking further away, it's tertiary bedrock. So these are just kind of things that I threw out there that we may have to look at or we may not. It just really depends on what sort of regional area that we're going to end up looking in.
Right, and then you had shown, I think, one of the earlier slides, kind of, what it looks like for mapping for like the UK and the US in comparison to what we have for information in Canada. And so as that kind of information or, research is done, then I would assume those maps, we would be seeing more detailed databases and information for offshore wind.
I was just talking with my manager this morning. We briefly went through this, and he agreed that we have big blank areas where we have a pretty good idea. We have some seismics, or we have some seabed photos, or some grab samples or something, but it's a lot of interpolation at this point. So yeah, basically when we can go in with some of our modern tools and collect seabed data and subsurface data, we generally tend to overturn a lot of the assumptions we have about that area. So yeah, that's priority number one, is just collecting data and then seeing what we have and adjusting our sort of regional hypotheses based on that.
Right. And I think, like you said, I think this announcement about the regional assessment is pretty exciting, because it will start to support some of that. So I won't keep monopolizing the time we have with my questions, and I'll move into the Q&A that's come in from the audience. So one of the first ones that came in was that you had mentioned seismic several times. How is the noise or sound intensive are the methods that are used to explore the ocean seabed and subsurface and to determine the geology? I don't know if you have a feel for that.
Yeah, so there is a range of acoustic active sensors that we can use to investigate both right from the seabed into deeper sediments. And generally, the deeper that you want to look, the more energy is required to penetrate deep into those sediments. What's fortunate for the offshore wind world is we're generally only concerned with those upper meters to upper tens of meters of sediment. So the seismic profilers that we use are generally of a lower energy source. So, and there, like I said, there's a whole range too. So in certain areas where there may be considerations for the level of ambient noise, there are we can sort of downscale the tools that we use to be more cognizant of the marine environment. But right up to the multi-beam echo sounders. So those are still acoustic tools, but there's been studies done on the impact on marine environments and sort of offset distances that you need to keep from marine, mostly marine mammals. So that work has been done to sort of lay out what is safe and sort of ecologically reasonable and responsible to do.
Right. Okay.
Yeah.
Next question. So do you have an estimated timetable for the Pacific Coast mapping?
Moving? Yeah, it's I don't want to say certainly, but I have assembled quite the consortium of authors. So it's kind of like once we heard all of the authors together, that product should be ready. And the anticipation is that it will be done by this calendar year, but please don't hold me to that. This fiscal year for sure, I will say that this calendar year is absolutely the goal, and I can see that as a reasonable goal.
Okay. Well, we'll check in with you too to see how things are going. Are you checking with us? This might be something that I think probably our members will be interested in as you're developing it. So, okay, and another, I'm just looking at my bigger screen here. So is the foundation suitability assessment going to consider drilled sockets with grouted piles as an alternative to driven piles or suction piles?
Yeah, so it's been a while since I've thought or discussed drilled sockets with grouted piles. I had a few sort of high-level meetings early on with subsea micropiles that was investigating and sort of developing this technology. And yeah, so drilled sockets with grouted piles, I'm not up to date with the industry, but I thought from the start it was cost prohibitive just compared to driven piles, just because of the way the industry is set up. But if that's your only option because you have bedrock, or if that's an option for floating offshore wind, then that is certainly a reasonable thing to assume. I think in some of my foundation suitability analyses, which is still pretty high level, I don't rule out bedrock in the floating realm because of that potential that could be an anchor for floating, but also the bedrock in Atlantic Canada, outside of that tertiary bedrock, which is sedimentary and can be quite flat, the bedrock could be very rugged, which, depending on scale, could be manageable with a drilled pile, but and drilled and grouted pile, but may just it's always a function of, yeah, you could probably use them, but maybe there's more efficient ways or more efficient areas that you could look at with more suitable foundation types.
Right. Okay, thank you. Next one, so we have a lot coming in, so I'm going to try to get to many of them as possible, just to put you on the spot the entire time.
Perfect.
So based on initial suitability analysis that's been conducted, some of the work that you have done, which areas profiled in Atlantic Canada have been identified as highest suitability using fixed platforms?
So I have to be very careful because I'm repeatedly reminded that I don't pick sites. As a government employee, I can only provide baseline information, and then industry are the ones that they take the direction and the specific data that they need to make those decisions. With that said, I can broadly say that I alluded to there are certain areas where there are deep suitable sediments, and they're particularly concentrated in those offshore banks. Now, that's to say also, though, that areas that are closer to the coast, there may be suitable sandbanks that we just haven't mapped yet. For example, Milne Bank off of PEI seems like a fairly suitable substrate for fixed bottom foundations. And there may be more sites like that along the Nova Scotia coastline that just haven't been mapped yet. But really, I will just kind of take a cheater's way out and say the most obvious places that we can put fixed offshore wind turbines are probably the places where there are already fixed bottom marine infrastructure in place. So that's Sable Bank, where we have piles that were installed for offshore oil and gas, and Northumberland Strait, where we have a whole series of concrete gravity bases supporting a bridge. So it's been proven that those places can support those types of foundations. Now there's differences between the engineering of what goes into offshore wind and what goes into those installations, but those are definitely two places where I would start looking.
Great. Next question, what kind of physical or biological water column monitoring is required prior to, during construction, as well as during operations of a fixed bottom offshore wind farm? Thoughts on that?
Well, so I would say that none yet, because we have not yet developed an environmental assessment or regulatory regime for offshore wind in Canada. So we don't have a regulatory framework from which we can say that you have to do this type of monitoring before you can install offshore wind. Right. Seems like a cheap answer, but just that we'll have to wait for the regulations to be developed for that to be answered.
Yeah, agreed. And actually on that, so there was a question that came up about regulatory, the time frame for regulatory regime. My understanding would be that GSC would not be as involved in that aspect, but I don't know if you have any, if there has been any engagement on your end, if there's anything you want to.
Well, I will point out that, and I think you guys are releasing, you're going to share in my slides, or the talk will be shared. On one of my earlier slides where I say signaled interest in Canada, there's a link to the NRCan website where they are developing these regulations. And so all that's the most up-to-date information in terms of a timeline for regulations being developed for offshore wind. So I encourage people to go click that link when they can.
Yeah, and to that point too, I mean, that's something we keep our members pretty engaged in terms of when there's the opportunity for the public consultation as they move into different phases of development. So for those of you that are joining, just keep a watch out for some of the things that we provide, because you'll have an opportunity through that as well. Okay, one other one. So will the industry, and this one I think you might be able to speak to, so will the industry avoid areas with seasonal sea ice cover, or are there favorable areas where ice engineered structures can exist? Yeah,
not an expert, unfortunately. And I will say that in our very preliminary document that we released early on, the first thing we released on this work, we pretty much drew a big box around Eastern Newfoundland and said, probably not going to happen here because of ice. But seasonal ice does happen in the Gulf, and there's of course tons of interest in the Gulf. So all I can say is that I know that there are ice resistant offshore wind foundations that have been built, and they're producing energy offshore Finland. They're not common, and I think they're quite high cost, but again, I can't say for certain. I can't quite remember the question, but yeah, seasonal ice is a consideration. Just it may drive up costs. You have to engineer for it, but it's not ruling it out based on that. There are engineering fixes that can manage that.
Right. Okay. And this one is I think, a pretty important one that just came in a few minutes ago. Is your geological research able to discover areas of archaeological remains or indigenous cultural interests that could complicate offshore wind developments?
For sure. So yes, short answer. Some of the survey methods that are employed, in particular side scan sonar, are almost tailor-made for that kind of investigations. So when things are being looked for at that scale at the seabed, that type of instrument often images those things quite well. And again, I can't say for certain if that will be included in the regulatory regime for Canada for offshore wind siting. But I would say that the geological tools that we have and can employ, depending on scale, sometimes it might be trying to hit things with a core or a grab, which may be challenging, but the imaging that we can do and the seabed sampling that we can do are the same techniques that they use on places like the Pacific coast, where they're actively doing that kind of archaeological prospecting. So yeah, we have that capability for sure. And it doesn't have to be specifically a survey or data collection dedicated to archaeology. It can be a part of a broader survey plan, but I certainly think it's important, and I hope it will be included with future work.
Yeah. Okay. Great. It's helpful to understand a bit better. And one thing I also wanted to just tease out a bit, and you may have touched on it, and I just wasn't certain, but in terms of, you mentioned, some sites that you looked at, there's not a lot of data yet. So obviously there needs to be more data collection to inform mapping and whatnot. But would you also, in terms of the criteria for how the GSC picks sites, like to look at, or areas, I guess I should say, instead of site, would you be looking, like, if you were looking for a particular industry, would you be also thinking of other criteria? So what I'm thinking of is like, electrical interconnection points, like what areas might make sense so that you're not obviously, so it's just as efficient as possible in terms of your efforts.
Right. Yeah. So totally, I warned you, I'm a geologist, rocks and sand, right? But this work is being done. So in-house CanMet Ottawa, which is a component of NRCan, they're doing these sort of multi-considerations analysis where that is a component of what they're looking at. And I will say that there's some really excellent research coming out of Dalhousie. Lucas Swan comes to mind. There's another person he works with, where they're doing this type of analysis, and even beyond grid interconnections and power demand, that they're looking at synoptic scale wind patterns and all sorts of things, and looking at this correlative analysis for where an offshore wind site may be best located to sort of offset some of the deficiencies in our grid, or some of the deficiencies in our broader sort of power plan, I guess. But again, I defer to them.
Yes, and I think I've seen some of those too. So for anybody that's like the Lucas Swan led study, or with some of the researchers that he works with, I think we've seen that one. And so I would also mention to anybody, on the webinar today, if there's interest in some of those pieces of work, we're happy to send the links to that. And then we also have some work that you've done as well, Jordan, that we have links to, that you sent, that you and your colleagues have done, that we can send out to anybody that's interested in kind of taking a deeper dive. So we're close to time. So this is kind of my last call for, does anybody have any other questions that you'd like answered? I don't see anything coming up. So I'm assuming that people are content with the information that they've received. But I would encourage, if there's questions for us or for Jordan, to just send a note along. Jordan provided his email, but we'll also be providing a link to the webinar for everyone that joined, and you can look at the slides as well when we send that. And so first, thanks very much, Jordan, for your time today. It was very helpful for me, especially because this is not an area that we, focus on as much as some of the kind of policy and engagement side of things. So it was very helpful for our knowledge, and I hope it was useful for those of you on the webinar today. And the other thing I just wanted to mention, while I have so many of you joining us, is that if there are future topics that would be helpful, we will be providing a series of webinars kind of to continue, on this kind of education piece for offshore wind, so that people get more knowledgeable about opportunities, but also challenges. So we are always looking for, ideas and topics that people are most interested in hearing about and are hoping to learn a bit more. So I just put that out there. Feel free to send us an email anytime. And thank you just everyone for joining us today. You'll get an email soon in the next few days from Amanda with all the follow-up information. Thanks, and we'll see you again soon.
All right, thanks. Thanks, everyone.